So hopefully I'm recording right now. Looks like it. Good. Hopefully everything went well with my first video. So we're going to finish up chapter 2 with a couple of one-dimensional kinematics problems. So I don't have the ability to show you writing out the solutions as I'm talking, but on D2L under the chapter 2 folder, so I've got two documents. I've got this presentation, and then I've got the solutions to all the problems. So I'm just going to be jumping back and forth between these two, talk you through the problems, give you some pointers on the algebra, let you know what I'm doing algebraically, what I'm solving for. Just make a couple points about, notation and kind of how I like to write out and solve these types of problems. So first problem is car coasting backwards downhill. It says speed of 3 meters per second, so I'm kind of already on the alert here because they're using the word speed, so I got to think about that. Driver gets the engine started. So the car's coasting, something happens, the driver starts the engine, and over a 3-second time interval, the car goes from moving down the hill at 3 meters per second and then moving uphill at 4.5 meters per second. Right, so the car's not running, rolling down the hill. They start the car, and then 3 seconds later, it's going up the hill at 4.5 meters per second. So I say if uphill is chosen as positive, what's the car's average acceleration? So I'm going to talk about like my coordinate system and how we choose it to make our lives as easy as possible for these types of problems. So it says uphill. If you ever took physics in high school, maybe you remember inclined plane stuff and their angles and all kinds of messy stuff. This is a situation that we can simplify. So I'm picking up the hill as the positive x direction. All right, so up the hill is the positive x direction. If I take my coordinate plane, my xy plane, I'm just going to rotate it counterclockwise a little bit. So my x-axis is now going to be pointing up the hill. All right, so I take any motion along the road or along the hill as positive x up the hill, negative x down the hill. And we're still in chapter 2, baby steps. We're not dealing with the y direction. We're just dealing with motion in one dimension. All right. So the problem says car is coasting down the hill with a speed of 3 meters per second. What the problem doesn't say is that the car's velocity is negative 3 meters per second. My coordinate system, up the hill is the positive direction, down the hill is the negative direction. So if I want to talk about the velocity vector, I've got to call it 3 meters per second as the magnitude and give it a negative sign because it's coasting down the hill. So I got a picture of the before, I got a picture of the after. The final velocity, I'm going to say v final, is positive 4.5 meters per second because after this 3-second time interval, I have a new final velocity, 4.5 meters per second. I'm asked for the average acceleration. So I got my picture, I start writing all my stuff down. What do I know? The initial velocity, the final velocity, the time interval that this velocity change occurs over, and I'm looking for acceleration. Right? Now I have this vector notation. Right? In the book you'll see these hats, right? These little arrows that represent vectors, vector quantities. In chapter 3 we'll talk more about vectors and get into some more sophisticated notation as we go back and forth between vectors and scalars. And occasionally, when I know I'm dealing with one-dimensional motion, sometimes I'll just get lazy and drop the vectors because I know I'm dealing with either positive or negative numbers. Not necessarily a good habit to get into, but something that I admit to doing every once in a while. So we've got these quantities. It's a pretty straightforward problem. I look back at my kinematics equations and I say, this is what I have, these 3 values I have. What am I looking for? I'm looking for the acceleration. So this one pops up, this one comes to mind. I can solve this for the acceleration. This is one equation, one variable to solve for. Again, very straightforward, just got to do a little algebra. So I'm going to use this equation from my kinematics equation slide, and I got to get t by itself, right? So I got to do a little bit of algebra. All these are variables, right? But we can move them around just like numbers, like we did, back in our high school math classes. So I'm subtracting v initial from both sides, right? Trying to isolate the variable a. So I'm subtracting v initial from both sides. I've got at on one side, v final minus v initial on the other side. Divide both sides by t. There you go. I'm getting lazy with the delta t's, right? So I'm saying t initial is 0. So delta t is just t in my case. So I kind of go back and forth between that sometimes. Just try not to worry about that too much. So now I need t by itself, or excuse me, I need a by itself. So I divide both sides by t, and what I actually end up getting is the definition of acceleration. If you go back to the slide that introduces acceleration, this is the definition, right? The numerator is actually delta v, right? So this is delta v over delta t. So now I'm looking back, and this might be a little bit unnecessary, but I use a kinematics equation. It was good algebra practice, right? Worked my brain a little bit, and got a nice expression for acceleration. You notice I did all this solving for a without substituting any numbers, any units in whatsoever. Okay, so I'm expecting, right, if I go back and I review my direction business between velocity and acceleration, I've got an initial velocity that's negative, a positive velocity, or a final velocity that's positive. I expect my acceleration to be in the positive x direction, right? My velocity is changing. It's going from this direction to that direction. The only way for my velocity to change from negative to positive is if I have a positive acceleration, right? Something's got to be causing that car to travel up the hill. So when I substitute my values in, again, I like to get into the habit of substituting my units, right? Because I'm just going to check my result into units and make sure that they combine to become the units of the quantity I'm looking for. Right, so acceleration, I've got v final, which is positive, minus negative 3 meters per second, right? So I'm subtracting this velocity vector from this velocity vector. So I'm actually subtracting a negative value from a positive value. So that's good, because this numerator up here tells me whether my acceleration is going to be positive or negative times a scalar. This is my vector quantity. It's going to be positive or negative. So I've got a 3-second time interval. My numerator comes out to be positive 7.5 meters per second. Denominator is 3 seconds. I've got a total, or I've got a resultant acceleration of 2.5 meters per second, right? Those are my units. Velocity, meters per second. So this is a fraction over a fraction. If you remember from your older math classes, you've got, this is actually s over 1. So I would multiply this fraction, this top fraction, by the reciprocal of this. So I'd have meters per second times 1 over second. I'd get meters over second squared. Those are acceleration units. Feels good. Got nice units. I've got a positive acceleration, and it's a reasonable acceleration for a vehicle that's originally coasting downhill and then get started. You think of a car in first gear starting and then going up a hill. That's a reasonable acceleration for this car. So I want to describe this thing, right? It's got a positive sign. It's an acceleration, so I got a vector hat. But just to give it a little bit more of a description, I'll just say it's in the positive x direction, right? It's positive, but the acceleration is actually pointing up the hill. Okay, so a little bit of verbiage to go with your value is always a good idea. Definitely can't hurt. Okay. So here's another situation. I got a skateboarder that's originally just on a flat surface. Skateboarder has a constant velocity and then starts up an incline. So if you're on a skateboard and you're on a flat surface and you start to roll up a hill, you're going to slow down, right? You're going to slow down, and then you're eventually going to come to a stop. And if you're good at skateboarding, you're going to be able to balance and then slide back down the hill. So what we're concerned with is how much time passes from when she begins to slow down to when she begins to move, from when she begins to slow down and when she begins to move back down the incline. So we know the acceleration, right? She's got a constant acceleration of negative 0.2 meters per second squared. Some people might call this deceleration, right? I don't like to use that word too often. I just like to give my acceleration a sign, call it acceleration, and then use the properties of vectors to kind of determine whether the object is slowing down or speeding up. Problem tells me she's slowing down. That's good news. Okay, so I'm going to have an initial velocity as soon as she hits the incline. She's got an initial velocity of 1.75 meters per second. She hits the incline, starts slowing down, 0.2 meters per second squared down the incline. So we're looking for a time interval, right? We're looking for a t. How much time passes from when she begins to slow down to when she begins to move back down the incline? That's kind of an odd question, so we got to look at that. Again, we're going to take up the hill as the positive x direction. So here's my skateboarder. Very similar situation to the previous problem, but the skateboarder starts up the hill and then reaches the top and then starts to slide back down. But this question, I'm only concerned with when she begins to slow down. That's when she hits the incline. When she begins to slow down to when she begins to move back down the incline. What does this mean? When does she begin to move back down the incline? That's when she reaches the very, very top, right? The highest point she can reach before the acceleration causes her to stop and then turn around, right? Because in real life, this is what's going to happen. Skateboarder is going to be going up the hill, going to have acceleration in the negative x direction, going to be slowing down, slowing down, slowing down, coming to a stop, and then changing direction, and then sliding back down the hill, right? And then she's going to speed up. She's going to speed up going back down the hill because her velocity is now in the negative x direction. Acceleration is in the negative x direction. They have the same sign, so she's going to speed back up, right? So she slows down on the way. Acceleration's opposite velocity. She's going to come to a stop, come back down. Acceleration same direction as velocity when she's going back down. I don't care about any of that stuff that happens after she comes to a stop because my question asks me this, right? So I've got a v initial. What's my v final? My v final is 0. When she gets to max height, that's when she stops moving up the incline and she begins to move back down. So I'm going to say v final is 0. Right? So I've got a good v initial, which is positive, a final velocity, which is 0, a negative acceleration, and again, this, I'm looking for t. Very, very similar. I got a nice kinematics formula that I just practiced using. Algebra is very similar, right? I'm getting t by itself now instead of a, right? So I'm looking for time, subtract v initial from both sides, then divide both sides by a. I've got t by itself. Again, I'm doing the algebra with the variables. I'm getting comfortable moving my variables around algebraically before I start to substitute numbers and units. So I've got a v final, which is 0, a v initial of positive 1.75. I've got an acceleration of negative 0.2 meters per second. So I've got a negative acceleration, a negative numerator, negative over negative, which is a positive. That makes me feel good about my answer so far because I know time is a scalar, it's positive. So I do my calculations. Negative 1.75 divided by negative 0.2 is 8.75. What are my units here? They're units of velocity over acceleration. Again, this is a good habit to get into. Take your units, the units from your numerator, units from your denominator, okay? Combine these, reduce them. Once again, I'm taking the denominator, flipping it, I'm multiplying the numerator by the reciprocal. All my meters go away, and one of my seconds go away in the top and the bottom, and I'm left with seconds, which are time units, right? So I got a pretty reasonable amount of time, okay? Skateboarders going at a decent rate initially, comes to a stop. It takes her about 8.5 seconds to come to a stop. Okay. Alright, so this is practice for another kinematics equation. I've got a change in velocity. Alright, I've got a car that's accelerating at a constant rate from 15 meters per second to 25 meters per second. That tells me the car's speeding up. So I'm expecting a positive acceleration. Okay, so I'm taking these two velocities. This problem isn't specifying what direction. So I get to, choose my coordinate system and say, are these positive velocities or negative velocities? It's only been a couple hours. I still hate negative signs. So I'm going to say all these are positive, right? So I'm going to say the car's moving to the right. Positive 15 is the initial velocity in meters per second. Positive 25 is going to be the final velocity. All right. I don't have a time interval, but I have a displacement. It says it travels a distance of 125 meters. I'm going to say that's positive, right? Everything's positive. The car's not changing direction, so I don't really have anything to worry about. We're looking for a time, right? And what I'll try and do is be more specific, on like assessment items. I'll say, how much time does it take? Because sometimes people will say how long, and then they think that's a distance or something like that. So I'll say, how far for distance, and like how much time for time, so we don't get too confused about that. How long does it take to achieve this speed? So I'm looking for a time interval. I've got a change in velocity, and I've got a displacement. Now what you'll see later on in other problems, this one's again pretty linear process here, but for some problems we're going to have a couple different ways of solving the problem based on the information we're given. So I try to at least give you one of those options and then like explain another way and maybe offer it up to you for practice. Sometimes I'll go through all of the options that I can think of. If you figured out a different way to do it, please by all means let me know, and if it checks out, I can share it with the other students and put it up on D2L and talk about it. Alright, so we've got an initial velocity, final velocity, we've got a displacement, right? But I wrote it as a change in position. Okay, I said the car is going to start at x equals 0 meters. That's my coordinate system. I get to pick my coordinate system. I say car starts at 0 meters, car ends at 125 meters. Okay. And also when I did this, I forgot that I actually include this equation in that equation slide, right? So I kind of did this nice derivation to show you where this comes from, and I called it a new equation, but I had already put it up there, but this is still very handy to get down, right? This is my dirt equation I talked about earlier. I'm dropping my vector notation sometimes. There's delta x, there's my average velocity times time, right? Displacement is velocity times time. So I wrote velocity as an average of two velocities, right? The car's initial velocity, car's final velocity. If these are the same, it's just v. It's just whatever that velocity is. If they're different, in this case, I've got an initial velocity and a final velocity. It's the average of those two velocities. So there's the 2 in the denominator, the sum of the velocities, and then the time. So this is what I'm going to use. Right? I'm going to use this because I've got everything that I need right here. So I'm looking for time. I'm going to take this and do some algebra to it and get t by itself. Get rid of this 1/2, multiply both sides by 2, right? Multiply both sides by 2. Now I've got a 2 over here. There's nothing over here because they cancel out. Now I've got 2 delta x is the sum of the initial and final velocity. That's its own term. It's in parentheses times time. Now I'm going to divide both sides by this entire quantity, v initial plus v final. I've got time by itself. I've got a nice expression. Right? I really like to see these. A nice expression for the variable for which you're solving prior to the substitution of values in units. So I've got my displacement, I've got my two velocities, be careful not to change this plus sign into a minus sign, right? We're dealing with final minus initial a lot, so just make sure you keep your sign straight. Don't make sign mistakes. So I calculate it positive on the top, positive on the bottom. I'm looking for a scalar time. That's great. I'm getting 6.25 seconds. So just a quick thing. I never found the car's acceleration. I know it's accelerating, but I wasn't asked for it, and I wasn't given it. Find the acceleration. Go back at your kinematics equations. Okay, we have time now, which is great, so we can use any kinematics equation now to find the acceleration. But let's say we didn't have this time. Okay, good practice would be find that acceleration first. See what the acceleration of the car is, right? Because a lot of these problems can be multiple parts. Find the acceleration first. That will open up the other kinematics equations to help you solve for time. All right, so that's another way of going about it. You're solving for something you're not being asked for, but you know, you won't hurt anybody by doing that. Okay, so practice that. Solve for the acceleration first with just this information right here. Find the equation that gets you acceleration, and then practice with some other kinematics equations you can use to find time. So that's good practice. Okay. So who's next? Here we go. Alright, so we've got a car traveling 20 meters per second. Driver sees an obstacle in the road. This is one of those two-step problems. You'll see a lot of variations of kinematics problems on WebAssign that kind of splits motion up into two parts, right? You might see two vehicles moving different rates. You might see a car like this where it's moving at a constant speed and then it stops, or it's moving at a constant speed and speeds up or slows down. So we're going to practice kind of splitting it up into separate parts and treating them as kind of separate scenarios and then combining them. So a car traveling at 20 meters per second when the driver sees an obstacle in the road. Driver takes 0.8 seconds to react. Okay, that's a very good quick reaction time. Okay, driver was paying attention, not texting and driving. Alright, so make sure we're not doing that. 0.8 seconds to react. Steps on the brake. As soon as the driver steps on the brake, slows down at a rate of 7 meters per second. Okay, I deliberately didn't put a negative sign there. Okay, I'm saying it slows at a rate. Okay, so we're going to have to handle that acceleration as a negative value. How far does a car go before it stops? How far? I'm looking for displacement. I'm looking for a delta x. Okay, so I'm going to split this up into two parts. I'm going to take the period of motion where the car is traveling at a constant velocity before the driver sees the obstacle. Okay, and then I'm going to solve for a separate scenario from the point where the driver reacts. Steps on the brake and starts to slow down and comes to a stop. So I'm going to split this up into two parts, and I'm going to find how far the car travels over both of those instances. So what I did, I solved for the displacement of the car prior to it braking first. All right. So I'm concerned with the 0.8 seconds that the car travels of velocity of 20 meters per second. So I kind of drew three pictures. Okay, this is t equals 0. This is when the car is moving at a velocity of 20 meters per second. This picture is after the 0.8 second time interval where the car is traveling at a constant velocity before the brakes are applied. From here to here, the car is braking. So the car has an acceleration of negative 7 meters per second squared, going in the negative x direction. Brakes are being applied. Car is slowing down. How far does it travel before it comes to a stop? So I've got a v final of 0 meters per second. That's that language again that I was talking about, right? It doesn't explicitly tell you final velocity of 0 meters per second, but it does tell you that it's coming to a stop. So the first part, it's a constant velocity problem. It's a constant velocity problem, so I'm using delta x is v delta t. Velocity's not changing for those first 0.8 seconds. So I use this equation right here. Delta x is v delta t. I've got a constant velocity, a time interval, meters per second times seconds. Seconds cancel out. I get meters, and I get a displacement of 16 meters. So something to think about. 0.8 seconds, you're going 20 meters per second. Find out how much that is. Cheat, use Google, see how fast that is in miles per hour, and then time 0.8 seconds. That shows you roughly how far that car would travel. Okay. So we've got 16 meters. Car hasn't applied the brakes yet. Braking, we're looking for how far the car travels while it's braking. Final velocity is 0. It's going to come to a stop. That initial velocity is the 20 meters per second that the car was traveling. I know the acceleration, right? So this equation is going to be useful for me. So I'm going to solve for delta x2. Why am I calling it delta x2? Because I've got two displacements. Delta x1, which I just solved for, 16 meters. Delta x2, the displacement while braking. So I'm looking for the total displacement. Call it delta x or delta xt for total, however you want to denote it. Delta x1 plus delta x2. Right? So I'm going to add up these two displacements. That is going to give me my solution. So I got to solve for delta x2. Algebra time again. Subtract v initial squared from both sides. Right here. And then I'm getting delta x2 by itself. So I divide both sides by 2 and a. 2 and a. So I've got delta x2 is v final squared minus v initial squared over 2a. Alright. So I've got my delta x2 isolated. Let's solve for it. 0 meters per second in for v final. Positive 20, right? 0 minus positive 20 divided by 2 times negative 7. Alright, again, we're keeping our signs straight here. I get a negative value in the numerator, negative value in the denominator. Still getting a positive displacement. That's good. Check these units, right? I've got meters per second in the numerator, but they're squared. And in my denominator, I've got meters per second squared. So my units in the top are meters squared per second squared. Distribute that square, right, across the quotient. Meters squared over second squared divided by acceleration units, meters per second squared. Flip that. All my seconds go away. One of my meters go away. I'm left with meters. Those are units of displacement. Good shape. Okay. So I'm taking 26 meters, or 28.6 meters, excuse me, adding it to those first 16 meters that the car was traveling. Right? My total displacement is the sum of these two displacements. Okay. So I get a total displacement of 44.6 meters. Okay. Again, that's half a football field. This person probably wasn't speeding, right? Was paying attention, had a very nice reaction time. Still traveled almost half a football field before it came to a stop. Okay, so here's your public service announcement for safe driving for the week. Okay, here's a very nice problem. I've got two vehicles. Okay, I've got two vehicles. One car is speeding. All right, one car is speeding. Let's say it's going down the highway 30 meters per second, and it passes a police car. All right, passes a stopped police car. So picture yourself, hopefully not speeding, but passing some point on the side of the highway. There's a state trooper sitting right there. You're passing a police car sitting at rest. This car speeding, police car comes out of the median, accelerates at 7 meters per second squared. Right? So I know the police car is at rest. I know the police car is at rest, and the police car accelerates, trying to catch up to the speeder. Speeder will say, speeder doesn't see the cop, right? We don't really see the police, right? They do a good job of hiding. So speeder doesn't see the police officer, keeps going, right? Keeps going at a constant velocity of 3 meters per second. All right, speeder doesn't notice the police car, doesn't slow down to pull over yet. So we're looking for how fast the police car will be traveling when it catches up with the speeder. Okay. So I'm going to pause quick. I'll give you maybe a couple minutes to try to set up this problem, and I'll come back to it. Okay, so pause, try and set it up, draw two pictures. Right, draw your speeder, and then draw your police car. Speeder has a constant velocity. Police car has initial velocity of 0, is accelerating. Okay. There are going to be a lot of unknowns. It's going to be very challenging to solve for one car independently. We've got two unknowns that we have to establish a relationship. Okay. So take a couple seconds, draw some pictures, write down as much as you know about the problem, and we'll walk through it. Okay, so where are we? Right, we got a lot of unknowns. Here's one thing I don't know. Right, I'm setting up my speeding car. Right, constant velocity. I got a velocity. That's great. Right, so displacement is velocity times time for the speeder. Right, speeder's moving at a constant velocity, not accelerating. There's only one equation. Now the trouble I have with this is that here's my speeder equation. That's the only one I got. I'm missing two variables. How far does the speeder go? Don't know. Are they asking us that? No. The time, right? How long, how much time does a speeder travel between when it passes the police car and when the police car catches up with it? Don't know that either. Alright, so I write a nice equation, but it doesn't get me anywhere, right? It doesn't have anything to do with the police car, right? No variables here deal with the police car, and I can't solve it. So it seems kind of useless to me right now, right? So I'm given all of these variables subscripts C, okay? C for car, right? C for speeding car, and then for the police car, I'm going to use lowercase p. Okay. So here are my two pictures. All right. I've got my speeder. What do I know about the speeder? Constant velocity of 3 meters per second. Speeder's acceleration is 0 meters per second squared. Right. Acceleration is 0. So picture this. Police car is like behind the billboard or something, right? This is x equals 0. Okay. Speeder and the police car are starting from the same position. We'll just say the police car saw the speeder coming, had his car, in drive, ready to go as soon as the speeder passed it. Okay, so as soon as the speeder passes the police car starts accelerating. It was stopped. It was at rest. So V initial of the police car is 0. We're given its acceleration. The acceleration of the police car, 7 meters per second squared. It catches up, right? It catches up over here. How fast is the police car going? So police car starting from rest has an acceleration. I write down all my equations for the police car. Alright? Not saying this is necessary, but all of these equations are applicable. Right? So I took the time, I wrote them all out, I gave them all nice subscripts. Okay, so all these equations are unique to the police car. Again, I don't have the time for the police car. I don't have the displacement for the police car. So I'm in the same situation for both of these cars. No displacement, no time. I don't know them, and I'm not being asked for them. So I can't solve any of these equations by themselves. But I have to look at some combination of equations that I can solve. All right, and the goal here is, if you're in a situation like this where it's not a straightforward like one equation, one variable, or like two equations, two variables situation, we've got to look at something that these two objects have in common. Okay. Now I'm looking, these all appear to be different quantities, right? I went through, I was really good about giving everything subscripts, right? None of these things in here look like I can substitute them in here, right? And vice versa. These are two different vehicles, right? What do they have in common? I go back to my picture. What do they have in common? They've got two things in common. They start their motion, right? This is my t equals 0, right? Remember my delta t business, right? This is t initial equals 0. I'm going to say t initial is 0 seconds when the police car starts to move. When the speeder catches, or when the speeder passes the police car and the police car starts to move. Police car is accelerating, finally catches up with the cop car, right? Or with the speeder, right? So here's one thing I got to recognize, that they start, right? This problem starts at the same time, right? Police car starts moving when the speeder passes it. Police car catches up with the car at some t final. So these two cars have the same t initial and they have the same t final. So they, in this problem, they have been traveling for the same amount of time. So what I'm going to say is delta t sub c is equal to delta t sub p. Right? That's great. So now I've got a time interval that two vehicles share. Right? So that's helpful. And maybe I could just drop this c and this p and this p, and I could find a way, right? I could find a way to substitute t in there, and eliminate some variables, and maybe get a nice expression for the final velocity of the police car. A better way of doing this is to recognize another property that both of these cars share. They don't just start at t equals 0. I get to call this x equals 0. So when the speeder passes the police car, that is the speeder's and the police car's initial position. And that's the same initial position when the speeder passes the police car. When the police car catches up with the speeder, we'll say he's in the left lane and the speeder's in the right lane, right? We'll say the police car has overcome the speeder, okay? So we can say they both have the same final position, right? Police cars in the left lane riding next to the speeder, saying, hey, pull over, pull over. So they're at the same final position. So not only is the time the same for both vehicles, but their displacement is the same, okay? So delta x sub c is delta x sub p. So what that means is any expression equal to delta x sub c is also equal to any expression that's equal to delta x sub p. Alright, so if I can get two expressions for these two variables that are solvable, I can set them equal to each other. Okay, so basically I'm going to be substituting two equivalent expressions in for delta x sub c and delta x sub p. Now the reason I like this method a lot better is because I come down, I go back to my equations, and I've got only one equation for the speeder, so I'm kind of limited there, right? So I've got one expression for delta x sub c. What do I have over here for the police car? Oh, I got this one that's already solved. That's nice, right? That one's already solved. That's good. Number 3 is already solved for delta x sub p. Right? So I think maybe, and I haven't tried this yet, maybe you could set this equal to this right here. Let's see what you get. Try that out. Pause the show, or the show. Pause the video and set this v sub c times t sub c. Set this equal to the right side of this equation. And since the times are the same, you should be able to cancel them out. Do a little bit of algebra, solve for v final. Alright, so I don't always take the easiest way out, and so I didn't really recognize that, so that's good. I just discovered another option. So hopefully you came up with the same value for the police car's final velocity that I did. I'm going to show you what I did. I set number 1, v sub c times t sub c. I set that equal to the right side of equation 3. Right? I set that equal to the right side of equation 3 because delta x of the police car equals delta x of the cop car. Right? So this I set equal to this. Why did I do that? Because I know the speed of the police car, or the speeding car, right? I know the velocity of the speeding car. I know that the times are the same, right? I know that the times are the same. And I know the acceleration of the police car. So I set equation 1 from the speeder equal to equation 2, or excuse me, equation 3. You just did equation 2. Equation 3 of the cop car. So I can simplify this. I know the police car starts from rest, so that term right there, that v initial of the police car times time, that whole thing is equal to 0. Okay, so that thing goes away. That's very nice. So now I've got v sub c times t is equal to 1/2 the acceleration of the police car times t squared. Right? I see a lot of people drop this t squared from that equation 3, so just be careful with that. So both sides have one t term, right? I've got a single term on this side, single term on this side. They both have t in them. Again, delta t is the same for both vehicles, and I'm going to cancel them out. Right? 1t goes away from here, 1t goes away from here. I get v sub c is 1/2 a sub p times t. So why am I doing this? I'm doing this to solve for time, right? Again, you probably, I think, you've already figured out the solution, so congratulations. So I'm going to take a bit longer way around, and I'm going to solve this for time, because once I solve this for time, I can take it. I can take that time and I can solve any one of these. Well, with the exception of number 4, I can solve any one of the first 3 equations, plug that time in, and get the final velocity of the police car. So I multiply both sides by 2. I get 2v sub c is a sub p times t. Right? So this looks a little weird, right? I've got a velocity of the speeder and the acceleration of the police car in the same expression. But that's okay, because we're relating the behavior of the 2 vehicles, right? Because they have this in common. So that's good. Divide both sides by a sub p. I've got a nice expression for t in terms of variables that I know. Okay. Cop car, or excuse me, speeder was 30 meters per second, constant velocity. Acceleration of the police car was 7 meters per second squared. Plug that in, I've got 8.6 seconds. So I've got the total time that the police car was traveling. Did they ask for that? No. But this is how I solved for it. I got the time, and then I came back up here to this nice equation, equation 1, because it's already solved for v final. Right? It's already solved for v final, and I can just plug time in. I know the police car is starting from rest again, so v initial is 0. I've got the acceleration of the cop car, so 0 plus 7 meters per second squared times the time, 8.6 seconds, and I've got a final speed, or a final velocity of the cop car of 60 meters per second. So take this information. You know what else I could do? I have this time, 8.6 seconds. Both the speeder and the police car are moving at a speed of, or moving for 8.6 seconds. Take this time, I can find how far they both traveled. Right? I can find the displacement of both the speeder and the cop car. Take this 8.6 seconds, plug it in there, multiply it by the constant velocity of the speeder, and you've got both vehicles' displacement. So I actually solved for everything, right? I got the displacement of both cars, I got the time that both cars were speeding or were traveling, and I got the final velocity of the police car. So I know everything about this problem now. Okay. Alright, so I hope this video isn't too long. It takes a lot of time for me to convert this to a file and then upload it, so I'm just going to continue to do this hopefully this helps. Hopefully this works out for you. Like I said, I wish I had a camera available to, like, film myself doing solutions. But feel free to reach out to me, email, Zoom. We can schedule a time if you need anything extra. So I'm just going to keep making these videos. I'll put announcements out on D2L. Work hard, study hard, stay in touch. Any physics questions you got, I am more than happy to discuss them with you. So that's it. All right. Thanks.